Dr. M. P. Jayaraman is an assistant professor in mathematics in L.N. Government College, Poneri. He has specialized on geometric function theory. With 14 years of teaching experience, he has handled topics on probability and queuing theory, discrete mathematics, random process, and engineering mathematics. Being a recognized supervisor for guiding PhD and MS students of Anna University, he is the reviewer of the journal Computer Mathematics and Applications. He has also written books on discrete mathematics and has also published papers in 28 international publications, in 4 national publications, and has presented papers in 2 international and in 2 national conferences.
Welcome you all for UGC lecture series in mathematics. In today's session, we are going to discuss about branch and bound method for solving integer programming problem. First, consider a integer programming problem. Maximize z equal to cx subject to the constraints ax less than or equal to b, x greater than or equal to 0 and integer. So, in this branch bound method also, first the given problem is solved as a continuous linear programming problem by ignoring the integrality conditions. So, by ignoring the integrality condition, solve the given IPP by considering as a continuous linear programming problem. Now, if all x are integers, then the optimum solution is obtained. Suppose at least one optimal solution is not an integer, then we have to improve that non-integer optimum solution as integer optimum solution. For example, consider XOR be the non-integer optimum solution. Then our XOR should satisfy the condition XOR less than or equal to XOR star plus 1 and greater than or equal to XOR star. If XOR is not an integer, then XOR satisfies this condition XOR dash less than or equal to XOR less than or equal to XOR dash plus 1, where XOR star and XOR star plus 1 are two consecutive non-negative integers. Hence, the feasible integer solution of XOR satisfies any one of these two conditions. If XOR satisfies this condition, then any feasible integer value of XOR must satisfy any one of the following two conditions. Those conditions are XOR less than or equal to XOR star or XOR greater than or equal to XOR star plus 1. So, XOR which satisfies this condition, then any feasible integer value of XOR satisfy any one of the following conditions. Now, these two conditions are mutually exclusive. This condition XOR less than or equal to XOR star and XOR greater than or equal to XOR star plus 1 are mutually exclusive, in the sense that both cannot be true simultaneously, and hence we cannot add these two conditions in a single LPP. Therefore, we should add this condition in a LPP separately and this condition in a LPP separately. This leads to branching the original problem into sub problem. Since these two conditions are mutually exclusive, we cannot add these two conditions in a single LPP, we have to add separately. This leads to the original problem becomes various sub problems. Now, this process of branching the given problem into sub problem is called branching method or branching process. This geometric process eliminates a part of feasible region that contains non-integer solutions. So, by this branching process, the original problem divided into partition into two sub problems. So, let me write those sub problems. The first sub problem 1 will be written as maximum z equal to cx subject to the constraints ax less than or equal to b and XOR less than or equal to XOR star x greater than or equal to 0. So, this will become our sub problem 1. So, by adding this constraints to the original problem, the sub problem 1 becomes maximum z equal to Cx subject to the constraint Ax less than or equal to b and XOR less than or equal to XOR dash. The sub problem 2 becomes this way. The original problem is maximum z equal to Cx subject to the constraints Ax less than or equal to b, and by adding this constraints XOR greater than or equal to XOR star plus 1 and x greater than 0, this will become our sub problem 2. So, the original problem split into two sub problem. The sub problem 2 is maximum z equal to Cx such that Ax less than or equal to b, XOR greater than or equal to XOR star plus 1, x greater than or equal to 0, and sub problem 1 is maximum z equal to Cx such that Ax less than or equal to b and XOR less than or equal to XOR star x greater than or equal to 0. This is our sub problem 1 and this is our sub problem 2. Now, by solving this sub problem as a continuous LPP, we can get the optimum solution. If the optimum solution does have an integer solution, then we should stop the process. Consider this sub problem. By solving this sub problem as a continuous LPP, if we get the integer optimum solution, then this sub problem should not be split further. Whereas, suppose consider this sub problem, if this sub problem does have an optimum solution, but a non-integer solution, again we have to branch this sub problem into two more sub problems. So, after branching the original problem into various sub problem and by solving the sub problem, we can get the optimum solution. Here, this branching process is continued until each problem terminates with either integer solution, integer optimal solution, or there is an evidence that it cannot yield a better solution. So, we will continue the branching process until each problem terminates with either integer optimal solution or there is a evidence that the problem cannot give the better solutions. Now, the integer valued solution among all sub problems which gives the most optimum value of the objective function is then selected as a optimal solution. Therefore, the optimal solution to the original problem is the integer valued solution among all sub problem which gives the most optimum value of the objective function. So, the integer valued solution to among all sub problem which gives the most optimum value of the objective function is the optimal solution to the original problem. So, in a branching process, first we will consider the given integer programming problem as a continuous linear programming problem by temporarily ignoring the integrity conditions. Then by branching process, we have to partition the given original problem into two sub problems. Now, we are interested in finding the optimal solution of the sub problem. If our sub problem has integer optimal solution, then further branching cannot be done. Suppose any sub problem have an optimal solution, but non-integer solution, in such a case further branching is possible. Now, we continue this process of branching until the problem terminates with either integer optimal solution or there is a evidence that the better solution cannot be obtained. Now, the optimal solution to the original problem is the integer valued solution of all sub problem which gives the most optimum value of the objective function. Now, let me explain the branching process with an example. Before that, let me explain what is a bounding process. Now, the process of branching the original problem into sub problem is a tedious process. For large problem, it takes lot of time to find the optimal solution to the each and sub problem. The main disadvantage of the branching method is we have to obtain the optimum solution to each and every sub problem. It is a tedious job. To avoid that one, we can increase the working process of branching method by the technique of bounding method. So, now let me explain what we mean by bounding method. The bounding procedure is whenever a continuous optimum solution of a subproblem yields a value of the objective function lower than that of the best available integer solution, it is useless to explore the problem any further. Therefore, such a subproblem is said to be bottomed and it is dropped from the further consideration. So, whenever a continuous optimum solution of the subproblem yields the value of the objective function lower than that of the best available integer solution for maximization problem, it is useless to proceed further. For such a case, we stop the further branching of this method. Thus, once a feasible integer solution is obtained, its associative objective function can be taken as a lower bound. This is for maximization problem to delete inferior subproblems. So, once a feasible integer solution is obtained, its associative objective function can be taken as a lower bound to delete the inferior subproblem. Hence, the efficiency of a branch and bound method depends upon how soon a successive subproblem are bottomed. So, the efficiency of a branch and bound method depends on how soon the subproblems are bottomed. So, this is the procedure for maximization problem. For minimization problem, the procedure is same except that of upper bounds are used. So, in the maximization problem, its associative objective function value will be taken as a lower bound to delete the inferior subproblem. For minimization objective function problem, the upper bound will be considered as the associative objective function to delete the inferior subproblem. Now, let me explain this concept of branch and bound method with the example. Suppose consider a integer programming problem, maximize z equal to 2x1 plus 2x2 subject to the constraint 5x1 plus 3x2 less than or equal to 8 and x1 plus 2x2 less than or equal to 4, x1 x2 greater than or equal to 0 and integers. Suppose the optimal solution of this problem is as follows: maximum z equal to 32 by 7, x1 equal to 4 by 7, x2 equal to 12 by 7. Here for this integer programming problem, by considering this as a continuous LPP, by temporarily ignoring this inequality integer constraints, we get the optimum solution as maximum z equal to 32 by 7 with the values of x1 equal to 4 by 7 and x2 equal to 12 by 7. Here the optimum solutions are obtained, but the optimum solutions are not an integer. So, x1 equal to 4 by 7, which will be written as 0 plus 4 by 7, and x2 is 12 by 7, which will write it as 1 plus 5 by 7. Among these two, the maximum fractional part is 5 by 7. In this x1, x2, the maximum fractional part is 5 by 7. Therefore, we will consider x2. So, x2 satisfies the condition x2 greater than 1 and less than 2. So, from this maximum fractional part, x2 satisfies the condition x1 less than x2 less than 2. Now, any feasible integer solution of x2 satisfies the condition x2 less than or equal to 1 or x2 greater than or equal to 2. So, from this inequality 1 less than or equal to x2 less than or equal to 2, any feasible integer solution of x2 satisfies these two conditions. Now, either of this condition is true. Now, we cannot add these two conditions simultaneously to our original problem. Therefore, we have to split the original problem into two subproblem by adding this constraints x2 less than or equal to 1 separately, we will get one subproblem, and by adding x2 greater than or equal to in one original problem, we will get the another two subproblem. Therefore, as far as this problem concerned, the subproblem becomes, this is our original problem. Now, from this original problem, our subproblem becomes this way. One condition is x2 less than or equal to 1. It leads to one subproblem. We name it as subproblem 1. And another one is x2 greater than or equal to 2, which leads to another sub problem. We name it as sub problem 2. Let us have a break. Welcome back. Before break, we discussed about the algorithm of branch and bound. Now, let me explain this concept with this example. Now, by making use of these two conditions, the original problem branched or partitioned into two sub problem. Now, our sub problem 1 is the original problem, maximum z equal to 2x1 plus 2x2 subject to the constraints 5x1 plus 3x2 less than or equal to 8 and x1 plus 2x2 less than or equal to 4, and by adding this condition x2 less than or equal to 1, where x1 x2 greater than or equal to 0, it becomes our sub problem 1. So, this is our sub problem 1. Now, by adding this condition to this objective function, then it will become our sub problem 2. So, sub problem is maximum z equal to 2x1 plus 2x2 subject to the constraints 5x1 plus 3x2 less than or equal to 8, x1 plus 2x2 less than or equal to 4, and by adding this constraints x2 greater than or equal to 2, where x1 x2 greater than or equal to 0, it becomes our sub problem 2. Now, by considering this sub problem as a continuous linear programming problem, we go for the optimum solution either by making use of simplex algorithm. Since this problem involves two decision variable, in order to obtain optimum solution, we can make use of graphical method also. Now, if this sub problem has an integer optimum solution, further branching is not required. Suppose sub problem 2 has an optimum solution but not an integer, again by the procedure discussed earlier, we have to split this problem into two sub problem. Now, this process continues till an optimum solution exists. So, with this idea, now we try to solve a problem. Use branch and bound method to solve the following: maximum z equal to 2x1 plus 2x2 subject to the constraints 5x1 plus 3x2 less than or equal to 8, x1 plus 2x2 less than or equal to 4, and x1 x2 are greater than or equal to 0 and integer. So, it is a all integer programming problem involving two decision variables. Now, by the method of branch and bound, we have to solve this problem in order to obtain the optimal solutions. Now, to solve this problem using branch and bound method, first we have to consider this as a continuous linear programming problem by ignoring the integrality condition. By ignoring the integrality condition, consider this as a linear programming problem, and we have to solve this linear programming problem either with the help of simplex method or graphical method. Since this linear programming problem involving two decision variable x1 and x2, in order to obtain optimal solution, we make use of the graphical method. So, we solve this problem by graphical method. Now, the constraints for the given problem is 5x1 plus 3x2 less than or equal to 8, x1 plus 2x2 less than or equal to 4. First, we will write the given LPP in a standard form. So, the standard form of LPP is maximum z equal to 2x1 plus 2x2 subject to the constraints 5x1 plus 3x2, and by introducing a slack variable s1, this will be written as 5x1 plus 3x2 plus s1 equal to 18, and for this constraint it will become x1 plus 2x2. By introducing a slack variable s2, it will become equality where x1, x2, s1 and s2 all are greater than or equal to 0. So, and of course, the original problem is x1, x2 are integer. So, the standard form of a given LPP is maximum z equal to 2x1 plus 2x2 subject to the constraint 5x1 plus 3x2 plus s1 equal to 18, x1 plus 2x2 plus s2 equal to 4, x1, x2, s1, s2 are greater than or equal to 0. In order to apply graphical method for this problem, first I will try to plot this curve in the graph. For that, I will just find the coordinates by taking x1 equal to 0 in the first constraints. So, x2 will becomes 8 by 3, and by taking x2 equal to 0 in this first equation by temporarily ignoring the inequality sign, we have, since x2 equal to 0, our x1 equal to 8 by 5. So, the first coordinate is 0, 8 by 3, and the second coordinate is 8 by 5, 0. So, now by joining these 2 points, we can plot this curve in the graph. Similarly, by considering this inequation, now by temporarily ignoring this inequality sign, this equation becomes x1 plus 2x2 equal to 4. In the same way, by taking x1 equal to 0, we will get our x2 equal to 2, so that the coordinates become 0, 2. And by taking x2 equal to 0, we have our x1 equal to 4, so that we get the coordinates of 4, 0. So, by joining these 2 coordinates 0, 2 with 4, 0, we can plot this curve in the graph. Now, by drawing this curve in the graph, our first idea is to find out the feasible region. Now, let me draw this curve in the graph. So, the first curve is curve joining the point 0, 8 by 3 and 8 by 5, 0. So, first point is 8, 5, 5, 0. So, 8 by 5 is approximately 1.6 something. So, this is a point 8 by 5, 0. And another coordinates is 0, 8 by 3. 8 by 3 is approximately 2.6. So, this is a point 0, 8 by 3. So, now by joining these 2 points in the graph, we got the curve 5x1 plus 3x2 equal to 80. So, I will join these points by a curve. So, this straight line is our curve 5x1 plus 3x2 equal to 18. Now, the next point is the point 4, 0 and the point 0, 2. Now, by joining these 2 points, by joining 4, 0 and 0, 2, we can get the curve x1 plus 2x2 equal to 4. So, we draw the curve 5x1 plus 3x2 equal to 8 and x1 plus 2x2 equal to 4 in the graph. We will get these 2 curves. Now, in order to get the optimal solution, first we look into the feasible region. Now, the given constraint of the problem is 5x1 plus 3x2 less than or equal to 18. So, this is our curve 5x1 plus 3x equal to 8. So, our area should be below this curve. And the second constraint is x1 plus 2x2 less than or equal to 4. Therefore, our area should be below this curve. Since x1, x2 greater than or equal to 0, we always look into the first quadrant only. So, the feasible region which satisfies this constraint 5x1 plus 3x2 less than or equal to 8 and x1 plus 2x2 less than or equal to 4 is the region which shaded here. This is our feasible region. So, our feasible region is area bounded by the curve OA, AB and BC. Now, the optimum solution for this given LPP occurs only at the vertices O, which is a point 0, 0, A, which is a point 2, 0 and C, which is a point 0, 2 and the point B. Now, we have to find out the point B, where B is the point of intersection of these 2 curves x1 plus 2x2 equal to 4 and 5x1 plus 3x2 equal to 8. Now, by solving these 2 equations, we can get the value of x1 and x2. Now, by solving these 2 equations, we will get our x2 value as 12 by 7 and x1 equal to 4 by 7. So, by solving these 2 equations x1 plus 2x2 equal to 4 and 5x1 plus 3x2 equal to 8, our solution is x1 equal to 4 by 7 and x2 equal to 12 by 7. Therefore, the coordinates of the point B is 4 by 7, 12 by 7. So, for this problem, the maximum occurs only at either at the point 0 or at the point A or at B or at C. Now, we will find our objective function value at this point. So, the first coordinate is 0 0. So, this is our coordinates and this is our objective function value, maximum z equal to 2x1 plus 2x2. So, the first coordinate is the point A is 0 0. At this point our objective function value is 0. The next point is A, which is the point 8 by 5 comma 0. So, at this function z equal to 2 into 8 by 5 plus 2 into 0, which is 16 by 5. This point will take it as O. Then the point B, which has a coordinate 4 by 7 and 12 by 7, our objective function value is 2 into 4 by 7, which is 8 by 7 plus 2 into 12 by 7, which is 24 by 7. Therefore, we have z equal to 32 by 7. And for the coordinate C, which is the point 0 comma 2, our objective function value is 4. So, at all the extreme points we got our z value. Here among all z value, the maximum z value equal to 32 by 7s, which occurs for the coordinates 4 by 7, 12 by 7. Therefore, the optimum value of the given problem is occurs at the point x1 equal to 4 by 7 and x2 equal to 12 by 7 and the maximum z value equal to 32 by 7. So, the optimum value of the given problem is x1 equal to 4 by 7, x2 equal to 12 by 7 and maximum z equal to 32 by 7. Here the optimum values are obtained, but the optimum value assumes a non-integer value. Our restriction on x1 and x2 should be an integer, but here we got the optimal non-integer value. Now, our aim is to convert this non-integer value as an integer value with the help of branch and bound method. Now, with the help of these two x1 x2 value, we try to obtain certain constraints, and by splitting the original problem into various sub problem, we have to convert the non-integer solution as a integer solutions. That things we will discuss in the next session. So, the optimal solution to the given problem is x1 equal to 4 by 7 and x2 equal to 12 by 7 with maximum z equal to 32 by 7. Now, we have to convert this non-integer solution into an integer solution using branch and bound method, which we discuss in the next session. Now, let me summarize the branch and bound method which we discussed so far. The first idea in branch bound method is solve the given IPP as a continuous linear programming problem by temporarily ignoring the inequality signs. The next idea is partition the original problem into two sub problems and solve the sub problems. So, the next idea is we have to branch or partition the original problem into two sub problem and solve the sub problem. The third idea is if any sub problems yields an optimum integer solution, it is not further branched, but if any sub problems yields a non-integer solution, it is further branched into two sub problem. The next idea is the branching process is continued until each problem terminates with either integer optimal solution or there is an evidence that it cannot yield a better solutions. The integer valued solution among all the sub problems which gives the most optimum value of the objective function is then selected as the optimal solutions. So, in branch bound method, the first step is we consider the given integer programming problem as a continuous linear programming problem by temporarily ignoring the inequality signs. Then we branch the given original problem into two sub problems and solve the sub problems. The next idea is if any sub problems gives optimal integer value, then the branching process is then the partition is stopped. Suppose if any subproblem does not give integer optimal solution, it should be further branched. Now, we continue this process until there is an optimal solution for the given problem, or there is evidence that no optimal solution to the given problem. Now, the optimal solution is the integer solution of all subproblem, which gives the most optimal value of the objective functions. Now, the problem is using branch and bound method, maximize z equal to 2 x 1 plus 2 x 2 subject to the constraints, where x 1 x 2 greater than or equal to 0 and x 1 is an integer. Thank you.